very special time in Salt Lake City.
Yeah, it's okay. Our big problem, as I mentioned earlier, is too much smoke in the air from the fires. But other than that, we're okay.
Yes, maybe it's for the first time for you to give lecture during such time.
Yeah.
It's maybe it's strange experience.
Yeah, it's much better to be there in person and see everybody in person. So I'm not a big fan of Zoom meetings, especially around the world.
Yes, you know, we did everything we would like to organize in person version, but what to do? So is our today life.
But and it's a sign of the times, things are getting bad. So we have to live with what we have.
Yes. Yes. It's night in Salt Lake City and evening in Japan. So it's all over the world, you know.
Yeah.
It's this management. This time it's difficult to find a right time, you know, for
Oh yeah, I fully understand. It's hard to get a right time.
One way to record those sessions, and after recording, it's possible to choose something, you know, and to follow any presentation that happened deeply in the night.
Yeah.
What to do? What to do?
No, it's the only thing you can do.
Yes.
But we can all hope that next time the weather or the pandemic will pass and we can get together and see each other in person.
Yes, yes, it's our hope. Every month, you know, every month we hope for better. We are waiting for better time. We hope that maybe next month, maybe month after month has to be better. But
we'll be lucky if we can do it by January.
First wave of COVID, second wave of COVID, third wave of COVID. This is unpredictable time.
Yeah.
What to do? And where is our Sergei figure? Yes, I see him. Everything is okay. Thank you, Sergei.
Yep.
Yes. And I am looking on a list of participants. Every minute, new comers. Our colleagues arrive and arrive. Yes. Yes, I see. Matvey, Sergey, we have 2 minutes. Okay? Right. Yes. We are waiting for 2 minutes. Oh. Hello, Lynch. How are you?
Good morning, dear colleagues. I'm fine, thank you. Thank you very much. Thank you.
Okay. We are ready. it's time we have to begin. Okay? Okay. Hi everybody. My name is Victor Chilenko. It's my great privilege to start this opening of our conference. Let me say a few words during our short opening. First of all, I would like to welcome all participants of our conference, all our colleagues in different countries. At the moment, we are in different time zones, but we are together, and this is most important. Let me say that 1 year ago, in previous August, we dreamed that in a year we will hold our regular conference in Nizhny Novgorod in a person version. It was 1 year before. Moreover, we were very optimistic in May that we will be able to organize in-person conference, or maybe we organize hybrid version of our conference. But in June, in Russia, it appeared so-called third wave of coronavirus. It's dangerous one. It's like delta modifications with scary consequence, and we lost any possibility to organize in-person version of conference or even hybrid version. Moreover, many international airlines are closed till now. There are some problems with visa issue and so on. Thus, we have to reorganize our organism work, and we orientated only for online version of our conference. Online version of conference is better than nothing. Science cannot wait. We have to communicate. Our magnetic area is active developed, so our communication is very important for our science. Our organizing committees in Nizhny Novgorod and Novosibirsk made a big job. We found everything, hotel money, we paid for ships, everything, but everything is behind. We have to work online. Let me ask our main organizers, Professor Fedyushkin, who is director of the Institute of Organic Metallic Chemistry in Nizhny Novgorod, and our co-organizers, Professor Matvey Fedin, who is director of International Tomography Center, to say a few words. I don't know who will be the first, Igor Fedyushkin or Matvey Fedin. Please. Igor.
Dear Viktor Ivanovich, dear participants, I see we now 43 participants which connected to the Zoom conference. So as Viktor Ivanovich said, I'm director of Razumov Institute of Heterometallic Chemistry in Nizhny Novgorod, and we intended to organize this conference offline in normal mode last year, but due to known reasons we could not do this. And I'm very glad that we can meet us today, this week, in Zoom format. And this is the 14th conference on molecular magnets and 9th Japanese-Russian workshop on open shell compounds. But both conferences will take place first time in Zoom format. This is an innovation in our case, and as I mentioned already, we would be very glad to see all of you here in Nizhny Novgorod this week, because this week Nizhny Novgorod celebrates 800th anniversary. And it was expected that President Putin will come here to celebrate this with citizens of Nizhny Novgorod, but he has another plans. He will meet Federal Chancellor Merkel in Moscow on Friday, August 20th. So I wish all of you successful work on this format. This format is known for all of us, and I hope it will not damage the scientific conversation which we used to do. So once again, welcome to this conference. I'm very glad that we are joined together. Thank you very much.
Thank you very much. I would like to join previous speakers also on thanking you all for joining us in this Zoom format. Despite probably all of us agree that in-person meeting is more interesting, more productive, more influential. Yeah, so we had to transfer due to COVID, and it's not a it really hurts, and I would like to remind you that this conference is dedicated to our colleague and friend Konstantin Ivanov, who was a previous director of International Tomography Center, and he sadly passed away exactly due to COVID, despite he was very young. He was not very much involved in molecular magnetism, but he was very much involved in spintronics, in open shell compounds, in this Russian-Japanese workshop. He participated many times in it. So the conference will be dedicated to him, and we have a special day Wednesday where we selected talks of his closest, let's say, colleagues and closest topics to his science. So Wednesday will be a special day dedicated to Kostya. And as you know, there are two conferences in one, in fact, and in previous meetings we had them sort of back to back, or one day was Japanese-Russian or Russian-Japanese workshop. And this time, because we are in Zoom and also because we are in different time zones, we decided we will not really separate these two events. They are kind of interleaved throughout the whole meeting, so do not be surprised, but we have, in a way, two conferences in one. That's it. And I would like also to say on behalf of all organizers, several technical things, technical notes about the conference. So the link to join the conference will always be the same every day. So you don't have to look for something else. And we will have also poster sessions on Monday, Wednesday, Thursday. They will be in the evening, and on Tuesday, to optimize, time zones again, it will be in the morning. And each poster will be in separate Zoom room, and you can enter, you can ask questions, and presenter will be waiting for you at that room. So it will be organized in this way. We will also do the recording of all sessions. We asked preliminary if anyone is against of that. Maybe some very preliminary results will be reported. Please let us know if you do not want to record your session. Otherwise, we are going to record them, and we will send you also the link. It's not really fully protected, but perhaps nobody except for our participants will know the link to Zoom channel, so you will be able to watch videos if you miss them during the conference because of your time zone and so on. So you will receive this link today, and it will be valid for the rest of the week. Then most of you perhaps know, perhaps everybody knows already how to work with Zoom, but just in case, you can always activate your microphone if you would like to ask a question, but better you first raise your hand in the reactions menu here at the bottom, and then the chairperson will see you and will ask you, let you ask your question. Then also, probably you notice that the schedule is kind of homogeneous. We do not have big break for lunch because lunch is a different time for everyone. So this is perhaps easier to remember when the sessions start. We have no cancellations so far. We hope we do not have any cancellations, but just in case, if anyone's lecture is canceled, we will not move the schedule. We will just have a gap there. So you will know when the lectures of your interest will start. Yeah, speakers for the next session can practice, of course, in the break before. And also, we would like to thank our sponsors. We have 3 sponsors. It's Bruker company, it's Cryotrade, and also Magnetochemistry Journal. And there will be at least three sponsored prizes for the good, best posters. So please attend poster sessions as well, and please be there if you're a presenter. And also, if you would like to kind of show your poster in advance for those who would like to see it in advance, please send it to us, to the organizing committee, and we will place it at the website just below the program at a glance. You can find it there. And also, if you have any questions, please contact us at our conference email. And that's perhaps all. We are almost on time, ready to start. Thank you very much once again. And I pass microphone to Viktor Ovcharenko, who is the chairperson of the first session. Thank you.
Thank you, Igor. Thank you, Matvey. We have to start with our first session. Let me introduce our first speaker, Professor Joel Miller. Joel is a distinguished professor of chemistry at the University of Utah. His research interests focus on the solid-state magnetic, electrical, and optical properties of molecular-based materials and electron transfer complexes, as well as the surface modification of solids. He has edited 17 monographs and published over 500 papers in this and other areas, and was this recipient of 2000 American Chemical Society Award for Chemistry of Materials and 2007 American Physical Society's James McCarthy Prize for New Materials, among several other awards. Everybody, even newcomers, knows that Joel is one among founders of our molecular magnetism scientific area. Today, Joel is going to speak about lithium salt tetracyanoethylene as a unique weak ferromagnet. Joel, please.
Thank you. Share the screen.
Yeah.
Yes.
First, I just want, can I be heard? I don't know what's going on. I want to thank really the organizing committee, Victor, Igor, Matvey, Sergey, everyone else. It's obviously we should be together and talk and see it and laugh and enjoy science together. We can't do that because of the pandemic. And this has created lots of chaos in terms of organizing a meeting. And you guys have done a wonderful job. I just wish we could all get together. And I think next time we will do that. So today I'm going to talk about one compound, lithium TCNE. And most of this work is done by graduate student Royce Davidson, and the more recent work is done by him. And so give him credit for the collaboration we've had in this topic. First thing I want to talk about is the reaction of alkali or any iodide with TCNE reduces TCNE to make a radical anion. And if you react it with sodium, potassium, rubidium, and cesium, you end up forming a compound that has a 2- dimer of TCNE, which is a very unusual species. This compound here has got a very unusual, very long carbon-carbon bond of approximately 2.9 angstroms, and is created by the overlap of the B2G singly occupied molecular orbital on each of the two fragments to give us what we have on the bottom over here, this 2-electron 4-centered bond. So it's a very unusual species from an organic chemistry point of view. However, when you react it with lithium, you end up with a completely different compound, and that is 1 lithium per TCNE instead of 2 lithiums for 2 TCNEs. Again, you form lithium triiodide. And the infrared spectrum is shown in red, and it's completely different than the green spectrum that we have for the 2- dianion, and completely different than in black for the isolated radical anion. But it is similar to what we see for mu4 TCNE radical anion illustrated in blue. So this material has a different infrared spectra and suggestive of forming TCNE radical anion that's bridged to 4 different cations. The structure was solved by powder X-ray diffraction Rietveld analysis. The data and fit is shown here in the upper left-hand side. And the analysis of the data shows that each TCNE radical, as predicted by the infrared spectra, in fact, bridges to 4 lithium cations. Each lithium cation bridges to 4 TCNE radical anions. TCNE radical anion is planar in the same plane of the 4 lithium ions. And this enables to form this lattice, which is a diamondoid-like lattice with the platinum sulfide structure, where we have a tetrahedral lithium surrounded by 4 lithiums, 4 TCNE radical anion, and each TCNE radical anion is surrounded by 4 lithiums. There's a lot of open space in this structure. And in fact, you have a second interpenetrating lattice illustrated in blue in there to do that. And the closest distance between TCNE is at the van der Waals limit, around a little more than 3.4 angstroms. And in fact, if you look at the 2 interpenetrating lattices, you can see the lithium is tetrahedral, and it's got the red lithium, it's got 4 red TCNEs. The blue lithium, it's got 4 blue TCNEs, and they form stacks and layers in the AB and AC plane. So this is the structure of the material, and both of those layers are mathematically and chemically equivalent to each other. So you have a basic feeling for the structure to do that. And if we look at any one of those 2 layers, the red and blue are interpenetrating lattices, so they're in different lattices. You can see the CN van der Waals interactions around 3.417 angstroms on one side, and a little bit larger, 3.46 angstroms on the other side. So each TCNE has 8 CN interactions with 4 TCNEs, and they form a layer either in the AB or equivalently in the AC plane. So nothing really sub van der Waals like the 2- dimer that's diamagnetic. If we look at the 2 different inner layers, we can see that the TCNEs are canted with each other by approximately 60 degrees. And a separation between them is a little longer, still in the van der Waals range of around 3.51 angstroms. So now we have a ballpark feeling for where the structure is. Now, interestingly, is the magnetic properties. That's the key talk of the meeting here. And if we look at the susceptibility versus temperature plot, as you drop the temperature, it rises as you would expect any Curie-Weiss behavior. But around at 22 degrees, you see there's an abrupt transition. And the question is this abrupt transition due to a magnetic transition or a structural change accompanying a magnetic transition? So we can look at the full magnetic data, and we can see above 120 degrees, you can fit chi t, or 1 over chi to the Curie-Weiss, and you can see chi t drops dramatically, but there's a rapid rise around 21 degrees, so indicative of magnetic ordinary setting in at that stage. Nonetheless, it was significant anti-ferromagnetic coupling as modeled by the Curie-Weiss theta value of minus 39 Kelvin for this material. So we ruled out a structural change. We looked at the unit cell parameters for A, B, C, beta, and the volume, and they monotonically increased from 16 Kelvin up to 300 Kelvin, and there's no glitch in the data suggestive of a structural transition. So this is totally a magnetic transition for this material. And we can see that if we look at the low field, field cooled, and remnant and zero field magnetization, there's a near coincidence of the field cooled and remnant magnetization and a bifurcation with the zero field magnetization, indicative of magnetic ordering approximately 21 degrees Kelvin for this material. If we look at the M of H curve, we do not see saturation. We see a small remnant magnetization around 10 EMU Oersters per mole. And this suggests a weak ferromagnet or a canted anti-ferromagnet, depending on what term you like to use for it. Using the term, of course, in either case, is that you can use the remnant magnetization, and the expectation, if it was fully magnetized at 5585 EMU Oersters per mole, and calculate through this equation the canting angle for this canted anti-ferromagnet, weak ferromagnet. And that canting angle is actually very small, approximately 0.5 degrees. So we've characterized this material as being a weak ferromagnet ordering around 21 degrees. We've eliminated the possibility of it actually being an anti-ferromagnet, because if we look at the AC chi prime and AC chi double prime as a function of temperature, we see absorptions for both of them, whereas you should not see chi double prime of T if it's in fact an anti-ferromagnet. And both are frequency independent, and you can see this pronounced absorption around 21, 22 degrees Kelvin. So we've characterized this material as a weak ferromagnet by many different magnetic measurements. Now we're looking now at the pressure dependence, and in this slide, we're just simply going to show the pressure dependence of the hysteresis loops. And you can see not much changes globally from virtually ambient pressure up to 9.73 kilobars, and even going back to almost ambient pressure. But you can see in the inset in the bottom right that in fact there is a change in the coercivity of it. So looking at this data, we can see the pressure dependence of the coercivity is evaluated, and I'll show that to you in a couple moments. We can also look at the remnant magnetization as well as the field cooled and zero field cooled, but the remnant magnetization is more important because we can extrapolate the magnetic ordering temperature from it, as since we do the remnant magnetization a function of pressure, we can determine the magnetic ordering temperature as a function of pressure. And I'll share that with you too momentarily. And here we have in blue, the magnetic ordering temperature goes up from 21 degrees to 23.2 degrees Kelvin, up to 9.73 kilobars reversibly at an average rate of approximately 0.23 kelvins per kilobar of pressure. The coercive field doubles, as you can see in green, as you go up. And in both cases, by releasing the pressure, both values go back to where they originated from at ambient pressure. So it's a reversible pressure dependence for this material. Now, we can also look at the canting angle. From looking at the remnant magnetization as a function of field and temperature, we could actually determine the canting angle as a function of temperature. We can likewise look at the remnant magnetization as a function of field and pressure and get the canting angle as a function of pressure. And so in fact, we can determine the canting angle alpha as a function of both temperature and pressure. And as far as I can determine, and people can tell me differently if they know examples, this is the first example in the literature where in fact we have a temperature and or pressure dependence of the canting angle for a weak ferromagnet. And here we look at the magnetization, remnant magnetization as a function of temperature and pressure for here. And you can see in both cases, initially they're at some finite value, depending on the scale you're looking at. And then it rises with a small increase in pressure or a small increase in temperature, reaching a maximum in both cases. And then on further pressure increase or temperature increase, the value decrease, and in fact, in both cases, are lower than the original value at ambient pressure and temperature as we have it. So we have the remnant magnetization as a function of pressure and temperature. And from this, of course, we can get the canting angle from it as a function of pressure and temperature. And that's illustrated in green as a function of pressure and illustrated in brown as a function of temperature. Note on top is the temperature scale and on bottom is the pressure scale. And they mimic, of course, the remnant magnetization from which they're derived from, as you would expect. And you can see, again, it rises up, reaches a maximum, and then comes back down. So there's a unexpected, nonlinear, non-monotonic change of both the canting angle as a function of pressure as well as a function of temperature for this material. Now, to be honest with you, we don't know why. We're in the process that we need some computational analysis, more than we have at the present time, but I'm going to give you a little insight that we have at the present time. So we have studied the structure of this interpenetrating lattice, both below TC at 16 Kelvin and approximately at TC at 20 Kelvin. The 16 Kelvin data is shown non-bolded and the 20 Kelvin data is shown bolded. And you can see the intra-layer CN interactions slightly increase in both cases for the ones at 3.42 to 3.46 angstroms and the other one at 3.46 angstroms going basically stays the same, just a slight increase. Now the interlayer between the two different layers actually have a slight decrease from that. And furthermore, there's a change in a cant between the angle, the planes, as I mentioned earlier, between this red plane and blue plane. It goes a little bit higher than 59.2 degrees. And also, which I don't show you, there's actually a twist in these planes going from 65, dropping down to 61.4. So not big changes, but there's only a 4-degree temperature change. And so we believe these changes play into why there is a increase and then subsequent decrease in the canting angles as a function of temperature and or pressure. And preliminary magnetic couplings calculated by Wanda Ova's group shows that the intra-layer coupling over here is actually ferromagnetic, and it's slightly more ferromagnetic, going from 16 Kelvin to 20 Kelvin, whereas the interlayer coupling is anti-ferromagnetic and goes from minus 15.4 to minus 18.9. So there's some structural changes leading to coupling changes, and some are ferromagnetic or some are anti-ferromagnetic. And this plays a complicated interplay between them, which likely leads to the change in the canting angle as a function of temperature. Now we can also get some more information and determine the phase diagram for this material. And if we look at the magnetization as a function of temperature, you can see at different fields, they go up with increasing field. And if you take the derivative dm dt, there's a minimum, and that minimum can be used to determine the phase boundary from the paramagnetic to magnetically ordered phase. You can also look at the bifurcation temperature between the field cooled and zero field cooled data, which is amplified by this example over here for the 6-degree data over here. And you can see in this particular case, it's at 21.1 Kelvin. And that also gives you a data point from the paramagnetic to the magnetically ordered phase. So we've accumulated a lot of data points for the phase boundary between the paramagnetic and magnetically ordered phase. We can also look at the maximum in chi prime of H as a function of temperature. And you can see at 1.8 Kelvin over here, it's fairly broad, suggestive of 2 maximum. And as you go down and up in temperature, the intensity drops, and it looks more like there's only 1 peak in there. And as a consequence, we can see a phase transition. And we've now analyzed this, which we'll talk about in a couple minutes, as having 2 transitions, one from the weak ferromagnetic phase to a spin flap in 2 dimensions, and then at slightly higher field going from the spin flap in 2 dimensions to a spin flap in 3 dimensions, designated SF2D and SF3D for this material. And you can see that's basically taken from the maximum. We've actually done it from the derivative. It's more convenient. And I'll just show you how we accumulated some of the data. And here is the data at 6 Kelvin in X's, and you can see the chi prime of T is simply shown here. And now we're going to fit it to a Gaussian to show the maximum for the lower field data. But you can see there's a divergence at slightly higher field, and we have to invoke a second Gaussian curve so that we have 2 Gaussian curves, 2 maximum, indicative of 2 transitions for this material for this. So we see the lower field one going from a weak ferromagnet to a 2D spin flap, and then a little higher field going from the 2D spin flap transition to the 3D spin flap transition. We can also see some of that data mimicked by looking at the change in chi t versus dt, d chi t, dt. And this is Fisher specific heat. And Fisher has convinced people that in fact, this mimics specific heat data, not chi versus t, but chi t versus t. And looking at the derivative, which I'm not showing, I'm just showing the maximum, which in fact is in fact the derivative of it. We're just not showing it. And we can get a transition that's at the weak anti-ferromagnet, weak ferromagnet phase boundary to do that. And if we look at all this data in 3D, we can see that in fact, we have magnetization on the y-axis over, well, the z-axis, temperature on the y-axis, and the x-axis is field. And we can see the manifold of data and the phase transitions. And using this data, we can amplify a 2D phase diagram where basically at higher temperature, we're in the paramagnetic phase. And as I mentioned, we have a phase boundary to the ordered magnetic phase over here. And in low field, we end up with a weak ferromagnet. And we have in blue over here the transition to the spin flap in 2 dimensions. And a slightly higher field, we have spin flap in 3 dimensions. And we have this region over here, which we've labeled C, which is clearly a very complicated interplay of all these phases, and that we don't fully understand this. And this is sometimes seen for magnetic materials of this type over here. So we've generated the phase diagram for this material. We've also determined the anisotropic field to be a fairly small value of 7 times 10 to the minus 6 kilo orsteds, and the exchange field at 27 kilo orsteds, and the ratio of the anisotropic field to the exchange field gives you a figure of merit for the anisotropy for the system, which is an incredibly low value of 2.6 times 10 to the minus 7. So this is an exceptionally weak, as you would expect for a first row element-based magnetic materials, with lithium, of course, being even lower mass than, of course, carbon and nitrogen, the other elements for this material. So just to summarize, our group has made over 10 families of magnetically ordered materials with many examples or several examples above room temperature. Haven't talked about any of these today, just simply talking about lithium TCNE of it, but we do have many other materials. And in fact, just quickly summarize, the whole community has made many examples of organic-based magnets. We have examples of ferromagnets, ferrimagnets, metamagnets, antiferromagnets, artificial antiferromagnets, and what we talked about today is weak ferromagnets or equivalently canted antiferromagnets. Also spin glasses and spin waves, chiral magnets, photomagnets have been made, and many applications have been made. And worldwide, people in other countries and other places have made major contributions. Many people are at this meeting today in Russia and Japan have made important contributions to this area. And try to convince you that you're already convinced there are many opportunities for all chemists and physicists to contribute to the synthesis, modeling, experimental data acquisition, and we always need new theories. And people have heard me talk, have heard me show this diagram now that was shown by the president of the Chemical Society to illustrate humorously the structure of manganese green salt, but we've taken this to a new level of spin coupling. And of course, the point, as I've made on many previous occasions, the key aspect is not only spin coupling, but people coupling, collaborations and interactions, as this meeting is enabling to do, not as well as if we were in person. You just bump into people in the hall and chat, but nonetheless, there's a good chance to collaborate with these areas. And I just want to end up by thanking you for particularly your kind invitation to attend this meeting remotely as it is, and of course, your undivided attention. And I have to give you a disclaimer. It's approximately 12:30 a.m. in Salt Lake City, and I've been up since 7 a.m. So I'm tired and I really can't participate as much as I would like to at this meeting, but I do wish you all the success, and I'm happy to open the talk for questions, although I have no idea how you do that.
Thank you, Chair, for your so interesting presentation. Topic is open for discussion. Maybe somebody would like to ask. Let me follow raised hands. Oh, yes. Professor Fedyushkin, please. Igor Fedyushkin. I don't know.
Oh,
Включите звук.
yeah. So I just, Professor Ovcharenko, I just want to thank Professor Miller for this excellent presentation. So I have no
Thank you.
Thank you. And especially last slide was very, very good. Yeah, so this cooperation not only between spins, but also between spins.
Oh, yes.
Yes, thank you.
Yes.
Dear Joe, I have question too. You know,
Sure.
What about other alkali metals? It's only for lithium derivative. Do you find any magnetization for other alkali metals?
Well, with TCNE, as I show in the slide here, is it gives a completely different compound, which is exceptionally interesting from organic chemistry point of view because of the long multi-center carbon-carbon bonds, but it in fact is diamond magnetic. So our attempts, and you will also get this type of structure with many examples of alkali metal, not alkali, but tetraalkyl ammonium compounds to do that. But we've not isolated any other compounds, although I do believe, and we have not studied it, but the lithium salt of TCNQ and TCNQF4 might have similar type of structure as the lithium salt of TCNE, which would be different than the other alkali, which are well characterized, because the lithium salt's not that well characterized. So I can't think of anything as exciting with the other alkali metals as with lithium. And just as a point of interest, although I didn't prepare myself to provide a slide of this, is that we and others have made a variety of alkali Prussian blue compounds with typically manganese and manganese hexacyanide. And the potassium, rubidium, cesium, and sodium salts give Prussian blue type compounds to do that. And the alkali actually, not the alkali, but the tetraalkyl ammonium compounds actually give a completely different set of compounds, which are really fascinating from a chemistry point of view, as well as a magnetic point of view. And of course, if you're doing that, go to lithium and make lithium. And in fact, lithium compound gives you the most interesting of all the compounds. But one of the reasons it's most interesting is that it has absolutely no lithium in the compound. It actually, it gives you a compound that has the cation, not an alkali metal, not a quaternary ammonium compound, but Mn4 OH4 with water as a cubic tetracation is the cation of the lithium made compound. And it's a most bizarre compound. And if you're curious, it was solved by Rietveld analysis. And I will argue it's one of the most complicated structures I've ever seen. But the fact of the matter is, lithium does things differently than the other alkali, magnetically and structurally. And we just have to study it and enjoy its fruits. I hope you have some new lithium compounds.
Thank you, Charles, for your answer. Excuse me, we have the third question from Professor Yanova. Katsuya.
Katsuya.
Oh,
Hi, how
yes.
are you? Ohayou gozaimasu.
Katsuya. Seichon. Your sound. Okay.
I can't hear you.
Oh, I cannot hear.
The
Something wrong.
sound is off.
Katsuya,
Can't hear you,
something.
Katsuya. I can't read lips. I don't know what happened.
井上君、ミュート、ミュート、ミュート。
Oh, yes,
Me
yes,
or
yes.
him?
Yes, okay. Yes, now it's okay.
My maybe yes. Now okay.
Yes.
Okay, now it's okay.
Sorry. Yes, this headphone should be connected to microphone, but I forget. Anyway, I just I'm interested in phase C in your phase diagram.
Yes.
Just between the
Me too.
TC and three-dimensional spin flip flop phase. You said this is a complicated and intermediate state.
Yes.
This
Which
case,
means we don't know much about it.
did you measure the frequency dependence? This phase should act in short range order, but they are intermediate long range order. Then they
Yeah.
should
That's a good point. We have frequency dependence, and the data that we have is frequency independent.
frequency independent. Oh,
Yeah, I just have to make. Can you see it here?
Yes.
So here's the frequency dependence, chi prime and chi.
Yes.
I see.
Yes, it's independent.
Yeah,
This is strange, but interesting.
yeah, yeah. We were wondering too, but this is part of the enigma of why this is a strange compound. And we consider this a unique compound because of this, the very low anisotropy for it.
Yeah.
So it needs a lot more work than we can give it to it at the present time.
But this case, if you have the nature of the spin glass, you should this compound should show the nonlinear susceptibility. Did you check the 3D?
No, we didn't look at that. Yeah.
It is maybe possible to understand.
Yeah, it may be possible.
Okay, thank you.
Thank you. Good seeing you.
Thank you, sir. Dear sir, let me thank you again for your so interesting presentation.
Thank you.
I know that it's night in Salt Lake City. So thank you. Bye-bye.
Bye-bye.
Thank you. Let me introduce our next speaker. Our next speaker is Professor Masahiro Yamashita. Professor Masahiro Yamashita is emeritus professor from Tohoku University, Department of Chemistry. He is an associate member of the Science Council in Japan, in which new directions for the sciences in Japan are discussed. He works and encompasses for important key areas in organic, hybrid, electronic states, nanosize and space, bottom-up and self-assembly, and nonlinearity and quantum effects. Everybody of us remember that Professor Yamashita organized fantastic ICMM in 2016. So it's my pleasure to announce the title of his today's topic: quantum molecular spintronics, spin qubits, and high density memory devices based on molecular magnets. Please, Masahiro.
Thank you, Victor. Can you hear me?
Yes, everything is okay.
Okay, so today my talk is here. So, yeah, our final target is one is a quantum computer. Second one is a highly density memory devices. So, first of all, I talk about the quantum computer. For realize quantum computer, spin qubits and coherence at room temperature is very important. So everybody knows classical bit and quantum bit. So every day you use a classical bit, 0 or 1, 0, 1, 0, 1. But qubit is a superposition of 0, 1. So if we use a classical algorithm, 0, 1, 0, 1, so the calculation takes 12 days. However, if we use a qubit quantum algorithm, the calculation takes 16 minutes. Huge progress. So then we must realize qubit. So qubit is, as I told you, minimum units for quantum information. As I told you, superposition was 0, 1, 0, 1. But for the quantum computer, low temperature is okay. But for the quantum sensor, this is applied for biological system, then room temperature is needed. So depending on the purpose, so low temperature is okay or room temperature is okay. So depending on the purpose. So there are some qubit candidate, photons, quantum dots, superconducting loops, trapped atoms, and neutron vacancy. But now molecular magnetism is very promising. So merit of molecular magnetism is a spin phase controlled by pulse EPR and high spin polarization of electron spin, high molecular durability. But the demerit is a short lifetime of superposition T2, spin-spin relaxation time. So this is a demerit. So then this is a definition of spin-spin relaxation time T2 and spin lattice relaxation time T1. So important point is that double T1 is larger than T2. This is a limitation, very important conditions. So as for the spin-spin relaxation time T2, so factor inverse to T2 is the first nuclear spin, neighboring spin, rotation of measure, and spin lattice relaxation time. So there is some example of T2 of molecular magnet. So more than 100 microseconds is enough. So some metal complexes over the 100 microsecond, and also room temperature, oxo-vanadium PC. So some metal complexes enough for realize a spin qubit. So and also spin lattice relaxation time T1. So factor inverse to T1 is the intermagnetic field and the spin phonon interaction. So most typical one is the oxo-vanadium compound. Spin is S equal 1/2. So this material here. So our target is MOF spintronics. There are 3 topics, but due to the time limitation, I focus on MOF spintronics. This means the suppression of intra and intermolecular vibration of oxo-vanadium TPP by using 3D MOF published in JAXA. So in the crystal structure, kappa MNT is planar. However, in the vacuum condition, so this kappa MNT is distorted. So lattice, crystal lattice, which suppresses intramolecular vibration. So I focus on the oxo-vanadium TPP. So in the zero-dimensional soft lattice, but we introduce a 3-dimensional morph of this oxo-vanadium TPP to make clear the factors of spin behavior influenced by critical lattice. So we synthesize step by step. Zero-dimensional starting material puts a zinc ion to make a 2-dimensional material, puts a bipyridine to make a 3-dimensional morph. Zero-dimensional, 2-dimensional, 3-dimensional, step by step, I synthesize. So this is a crystal structure. In the zero-dimensional compound, vanadium distance is 8.6, but in the morph, vanadium distance is 13 angstrom. So this is EPR spectrum, 3-dimensional morph. This is zero-dimensional starting material. G value is same. So this means the same electron structure, independent on the dimensionality. So this terahertz spectra, zero-dimensional compound, you can see very sharp peak around 67 wave number is observed. This is a mixture of vibration between metal ligand and deformation of the ligand. So molecule is very soft. However, in the three-dimensional morph, no peak, we succeed to suppress the lower energy of deformation of the 3D morph molecule. So 3D morph is very rigid. Then we can suppress deformation. So this dependence of T1 and Tm. So you can see, even at room temperature, quantum coherence is observed. And also Rabi nutation. We observe the Rabi nutation even at room temperature. And Rabi frequency depends linearly to the relatively intensity of oscillation field. So a brief summary. In the case of 3D morph complex, Rabi nutation and qubits were observed due to the rigid lattice at room temperature. So skip the second and third topic. So let's move to the second topic, highly density memory devices. First, single molecule memory performance by single molecule magnet, metal fluorine single molecule magnet encapsulated into single carbon nanotube, metallic conducting single molecule magnet with negative magnetic resistance. Every day you use a classical magnet. Every time we use a single molecule magnet. Why should we use single molecule magnet instead of classical magnet? Answer is to overcome Moore's limitation. Everybody knows Moore's law. Every 1.5 years, memory capacity increased twice. So now 201 around here. So in order to increase the memory capacity, we must make the classical magnet hard disk drive make smaller into nano size. However, classical magnet doesn't work in the nano size. Then we must use a nano size cluster, such as a single molecule magnet. That's why we use a single molecule magnet to overcome the Moore's limitation. So everybody knows what is single molecule magnet. So classical magnet, three-dimensional ferromagnetic ordering, but the single molecule magnet works as one magnet. So perfectly different. So then typical one is a classical magnet is a floppy disk. So capacity is 10 to the 9th bit. However, single molecule magnet works as one magnet and works as one memory. Then one molar has 10 to the 23rd. Huge progress. We must realize highly density memory devices by using single molecule magnet. So also Spintronics. Last century, electronics is based on the freedom of charge of the electrons. But the Spintronics in this century, based on the freedom of charge and spin of the electrons. So then Spintronics has much advantage. For example, no volatility of information, high operation speed of nanoseconds, high information density, low consuming electric power. This is a big advantage. So there are several magnetic resistance effects. So typical one is the giant magnetic resistance and tunneling magnetic resistance. Every day you use this magnetic resistance and CMR, BMR, EMR. Every day you use GMR, TMR in your own computers. So also I use a scanning tunnel microscopy, STM. STM is an instrument for imaging surface at the atomic level like this. And also scanning tunnel spectroscopy, STS. This provides information about the density of state. So you can see here. So the tunnel conductance, DIDV, is directly proportional to the sample dose. We usually use STM and STS. This is a condition of STM and STS. And we focus on double-decker fluorine terbium. This is a single molecule magnet. So neutral. This is very easy to sublimate. So this is made of the 4F8 terbium 3+ and pi radical and total 3+ and 3- total neutral. So we determine the crystal structure. Terbium, dysprosium, yttrium. Upper fluorine and lower fluorine distorted around 41 degrees due to the steric hindrance. So first, single molecule memory performance by single molecule magnet. So every day use a hard disk tunnel mount resistance. Spin is parallel, high conductance. Definition is 1. Spin is anti-parallel, low conductance. Definition is 0. 1, 0, 1, 0 switching by the external magnetic field. So every day use this tunnel mount resistance in your own hard disk in your computer. So how to write and read one memory in the single multi-magnet? For this purpose, we use a STM. TIPS is electrode 1, sample is electrode 2. So as I told you, this TMR. So and the spin of the chips is, and the spin of the single multi-magnet parallel, a high conductance, anti-parallel, low conductance, switching, high conductance, low conductance, high conductance, low conductance, switching in the TMR. So we must visualize for understanding. So spin of the chip is down, and single multi-magnet spin is down, 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 then high conductance, and spin is down, up, and the DIDV is small, then color is bright, dark, bright, dark, down, up, down. So we must realize. So, and also we must prepare the chip for the spin polarization. We usually use a platinum iridium tips, and cobalt bulk is a ferromagnet, but the one cobalt atom is paramagnet. We put platinum iridium tips, take one cobalt atom, this is a paramagnet. So this is a tips, platinum iridium, one cobalt atom. So this is a result to check the ability of memory in the classical magnet by using the TMR. You can see this is a cobalt island, then classical magnet. Here is a bright, then spin is up. Here is a dark, spin is down. So spin up, spin down is visualized like an Oslo game, black, white, like a bright and dark. So spin up, spin down. So, so we can see the movie. Now, external field is minus 1.0. So spin down, so color change. So spin down, spin down. We use a TMR and we change the external field. A spin up or spin down, the classical magnet spin change up or down. So we put the information upspin or downspin in the classical magnet. So now in the cartoon, so from the beginning, down, down, spins down, down. With the increase of field, up, down, and up, like this, and up, and up, down, down, down. So his state is observed. So we must realize single molecule magnet memory devices on the gold surface and ferromagnet, cobalt, and single molecule magnet. This is one single molecule magnet. So okay, you can see this is one single molecule magnet. External magnet is 2.5 around here. Now spin is down, dark color, spin is down. Okay, we decrease the external magnetic field. Okay, now external magnetic field is decreasing. Now around here, dark, dark color, dark color. Now bright color. Now spin is here. Spin change. And down, colors change. We see the from the spin down, decrease the magnetic field, spin up, spin down. We put the information, one spin into the one single molecule magnet, up spin or down spin. Now darker, spin up. Now spin down, here. And now darker, spin up. So we realize single molecule memory devices by using the single molecule magnet. So I'm sorry, this is Japanese, but we since the monolayer single molecule magnet by using the spin polarized multi stem chips, we slip the chips and put the information and slip, read the information. So this real use for the single molecule memory devices. Let's move the single molecule magnet encapsulated into single carbon nanotube. So single carbon nanotube is a metallic and semiconductor mixture, 8 to 20. So inserted single working magnet, conduction electron and local single magnet interact. So this is a new Spintronics. So we inserted the single working magnet, metal fluorine single working magnet, and double deck after signing. So this is a motif. So high vacuum condition and high temperature, a few days and wash outside. So this starting material, he says observe, this is actually single working magnet. So we encapsulate in this into the single carbon nanotube. So this is a result, TEM image. So you can see spot is observed. This is encapsulated single working magnet, metal fluorine single working magnet, like this. So this is EDX, scandium and dysprosium included. And this is a hard stem, bright spotted single working magnet, metal fluorine single working magnet, hard stem. This Raman spectroscopy. This is very powerful. So you can see Raman shifted before and after encapsulation because the charge transfer from the metal fluorine to outside single carbon nanotube, charge transfer occurred. Then Raman shift is observed. So interestingly, coercitivity before encapsulation 0.5, after encapsulation 4 kilo almost 1 order increase. This means that quantum tunneling is suppressed. So quantum single working magnet is enhanced. I'm sorry, it is Japanese, but we put one carbon nanotube by lithography, put the electrode. So this is a gold electrode. Okay, this this gold electrode, and this single carbon nanotube, parallel and perpendicular, no magnetic resistance. But we switch from gold to nickel. You can see magnetic resistance observed. Very small, 0.37. But we observe the magnetic resistance for the first time in the metal fluorine single working magnet inserted in the single carbon nanotube. And also a magnetic field Coulomb blockade. This carbon single carbon nanotube, and this is a palladium electrode. This is a motif of the double deck after signing inserted. This is the devices before encapsulation, after encapsulation. We compared before and after of the Coulomb blockade. So before encapsulation, Coulomb oscillation, Coulomb blockade oscillation is observed, and we switch the external magnetic field. No difference, no magnetic effect because no spin in the single carbon nanotube. But after encapsulation here, so irregular Coulomb blockade observed, and we increase the magnetic field. Magnetic peak is shifted. So this means that conduction electron and the spin flip interact. So actually, single working magnet inserted in the single carbon nanotube. So finally, I talk about the metallic conducting single working magnet with negative magnetic resistance. So usually single working magnet behavior is very low temperature, and electrical conductivity is high temperature. We must hybridize these properties to realize the negative magnetic resistance. So we realize conduction path and the local single working magnet interact to show the negative magnetic resistance using these molecules. So in this case, we use a donor is a BEDO, organic donor, and the single working magnet cobalt single ion magnet combined by the electrochemical method. Yes, this compound. So this conduction path BEDO and the single working magnet interacted. So this electrical conductivity. It shows a metallic behavior. Around 60 Kelvin, metal initial transition observed. And again, 6.5 Kelvin, metal initial transition, second metal initial transition observed. What's happened in the past? We calculate, you can see, Dirac cone is open, observed. So then this is a Dirac cone. Then what is second metal initial transition? What happened? We measure magnetic susceptibility. So antiferromagnetic interaction observed. So then conduction electron and the low class magnet interact with the antiferromagnetic interaction. However, below antiferromagnetic interaction temperature, we observe the heat states because the single magnet survive below antiferromagnetic temperature. Then frequency depends observed below 6.5 Kelvin. So because single magnet survive, then the single magnet and the conduction electrons interact, deeper interaction. And also negative magnetic resistance is observed due to the conduction electron and localized single magnet. So we do the pressure dependence. So first metal initial transition is suppressed, but second metal initial transition is not suppressed. But you can see electrical conductivity increase more than 1,000 Siemens. This is the highest conductivity and the first metallic single magnet and deeper interaction to show the negative magnetic resistance. Today I talk about the two topics, quantum computer and high density memory devices. So, and I acknowledge my many co-workers and many co-workers. So thank you for your kind attention. Thank you.
Thank you, Masahiro, so much. Let me, yes, Matvey, please.
Thank you very much, Professor Yamashita, for a very interesting talk. I have one a little bit general question. When you speak of long coherence time, this is your very first topic. When you speak about long coherence time at room temperature, how do you solve the problem of initialization of your qubits at room temperature? This is a general question, but maybe you have some ideas.
Yeah. Good question. So as I told you, we must increase the T1 and the T2, spin glacial time and the spin lattice glacial time. We must suppress, okay? So then usually, so T2 is influence of the nuclear spin or neighboring spin or rotation or spin lattice relaxation. And also T1 is influence in the inner magnetic field, nuclear spin or magnetic dipole interaction or spin phonon interaction. We suppress these interactions. Then we must realize room temperature spin qubits, long coherence time, and also Rabin nutation observed even at room temperature.
This is of course true. What I mean is that at room temperature you have populations of 2 levels of electron spin. So usually people go to a very low temperature in order to have a negligible population of the upper level. And how do you solve this at room temperature?
Your question is very important, but as I told you in the first, for the quantum computer, low temperature is enough. For the quantum sensor to apply the biology system, then room temperature needed. But if I focus on the quantum computer, so low temperature is enough, then population it doesn't matter.
Oh, okay, I understand. Yeah, thank you very much.
Yes, let me see. Raise hands. Again, Masahiro, let me ask you. When we discuss quantum computing, of course, we start usually with chance criteria, how to prepare ground state, readability, and so on. But maybe it's time to introduce additional criteria concerning chemical stability. Maybe it's necessary for you to speak about encapsulation, as in your case, for example, because temperature conditions, there are oxygen molecules, water molecules, and it can be dangerous for working device, for working block. What do you think? It's for discussion, you know, to add some chemical criteria.
I'm sorry, I cannot catch. This target?
When we discussed this problem concerning quantum computing, we discussed usually physical criteria and never chemical criteria.
Okay.
Sometimes encapsulation may be very important because your working path can be very sensitive to small molecules like oxygen, like water molecule. Maybe sometimes it's necessary to take into account chemical criteria too.
Yeah.
What do you think?
Yeah, a good question, but very difficult to realize that kind of systems. So I try many things. But not so easy.
Yes. Okay. Dear Professor Masahiro, thank you for your presentation.
Thank you.
It's time. Thank you. It's time to go to another presentation. Our next speaker is Guillem Aromi. Let me introduce Guillem Aromi is full professor of Department of Inorganic and Organic Chemistry, University of Barcelona. At the moment, he is director of the Institute of Nanoscience and Nanotechnology. Today, he is going to speak about spin-based multi-qubit quantum gates using heterometallic Lanthanide molecules. Please, Guillem, it's your time.
Thank you very much, Professor Obrashenko. Can you hear me well?
Yes.
Okay,
Yes.
Excellent. So I thank you for this nice introduction, and I especially thank the organization of this meeting, especially Professor Matvey Fedin for this very nice invitation. I really appreciate it. It's for me a great honor and pleasure to be here, have the opportunity to speak about some of the research we're doing in Barcelona. The only regret is that we cannot do it in person, that we cannot interact personally, and also get to know the wonderful city of Novosibirsk, and hopefully we can do it sometime soon. So I will then start my presentation first by sharing my screen. Okay, so I hope you can see well this presentation. Today I'm going to talk about the use of chemistry to produce heterometallic lanthanide complexes with the intention to portray them as possible quantum gates for quantum computing. So I was fortunate enough to have Professor Yamashita before me giving a very good introduction on the principles or the main guidelines of quantum computing. So we all know that quantum computing is going to provide wonderful advantages compared to classical computing, not only in terms of speed of calculation, but also on the nature of the problems that we can address using this new technology, which will provide these advantages thanks to the use of the resources of quantum mechanics with respect to classical computing. So the information is encoded in quantum computing by a qubit, which is a quantum system that can be in 2 quantum levels. So we do not have a physical system that contains the information in 2 physical states, but we have a quantum system that contains the information in 2 quantum systems, with also the additional advantages of quantum mechanics. For example, the fact that we not only have 0 and 1 as 2 states, but also any superposition of these 2 states, as is natural in quantum mechanics, offering resources and advantages such as quantum parallelism, for example. So those are the criteria that any quantum system should fulfill in order to be able to embody a quantum bit. As I mentioned, 2 quantum levels, the ability to initialize, something that was raised before. I presume that we can initialize not only by lowering the temperature, but using other mechanisms, such as, for example, post-DPR. Scalability, so we have to be able to integrate many qubits to produce complicated algorithms. Long coherence times, as this is evident, or information has to be around long enough so we can process it in the way we desire. And of course, addressability. We need to be able to introduce this information, initial conditions or other states, and also the ability to read this information. So as I was mentioned, we have, in nature, there are many quantum systems that we can try to use for implementing this technology. And so today I will be focusing on lanthanide ions. Lanthanide ions have the possibility to embody qubits because they have very often in the ground state a two-level system that is very well isolated from the excited states. Usually they have the possibility to produce good quantum coherence. And of course, we as chemists love this option because chemical versatility allows us to tune and tailor properties that to our advantage. And this is what we like as chemists. So here is an example from the literature by Professor Pelikos, where they showed good quantum coherent properties for this ytterbium coordination compound. But also there are other advantages or other interesting features that lanthanides can provide. In particular, lanthanides that do not have a spin orbit coupling. So this is a gadolinium. Of course, this is the least lanthanide metal that we have in this period. But we can take advantage of the large spin ground state that this metal has. So to use the 8 here 7 halves, to use the 8 states that are engendered from crystal field anisotropy, 8 states that are unequally spaced, so can be addressed individually. And so in this case would allow us to realize 3 qubits within one single metal, because these 8 states produce the computational basis of 3 qubits. So these are these 3 qubits, and for example, we can use these as to realize 3 qubit quantum gates. One of them is called Toffoli, or control not, which flips the spin of a target qubit if the first 2 qubits are in the position 1. And from these notation experiments using pulse TPR, we can see that indeed on this resonance we can realize or put our system in any of the possible quantum superpositions. So this coherence and this manipulation abilities were demonstrated in this paper not so long ago. So if one gadolinium ion can contain 3 qubits, maybe it is possible to use chemistry to increase the number of qubits that we can manipulate and use using gadolinium. For example, if we increase gadolinium, the number of gadolinium ions and make a dinuclear system, we could think about having a 6 qubit system if we have 2 different ions and they are connected through a weak interaction. So chemistry allows us perhaps to produce these kind of systems. And if we fulfill these conditions, we would be able to generate a set of 64 unique states that could be addressed individually and therefore generate a 6 qubit system. So chemically, we can think about a way of putting 2 lanthanide metals together using ligands that are asymmetric, like this ligand here we made in our lab some years ago, that has 2 types of coordination pockets. And so by linking 2 lanthanide ions with 3 of such ligands, we inequivocally put 2 lanthanide ions with 2 different coordination environments, and therefore fulfilling the asymmetry condition. And so we should make sure that this is a bridge that ensures an appropriate magnetic exchange so as to generate this 6 qubit system within one molecule that I mentioned. So if I will use this system to make all the series of coordination compounds of lanthanides for the entire period, we've been able to actually obtain the crystal structure of all of them. We've been studying these systems over the years. We've realized a few interesting features on this series of compounds. For example, Well, we see that if we compare the bond distances for the entire series of complexes, the trends of lanthanide contraction are fulfilled. But one interesting thing is that we see a systematic difference on bond distances, on average bond distances from one side to the other side. So even if in both sides we see the lanthanide contraction, this gap between bond distances from one side to the other is maintained throughout the entire series. So there is one position on this scaffold that favors larger metals compared to the other position. So of course, this can be exploited to produce in one-pot reactions heterometallic lanthanide systems as long as we mix together two metals that have different sizes, because the system is then going to select the larger metal to put it in one position compared to the other position, which is going to be reserved for the smaller metal. So this, in fact, is a coordination system that offers this wonderful possibility, and it works remarkably well. We've produced many different systems and studied them from various points of view, and used a large array of techniques that allow us to say that for many combinations, this selectivity is very high. It becomes a bit smaller as the metals become closer in size. And we've realized, especially through mass spectrometry and also confirmed by calculations, that when we move from the solid state to solution, this selectivity decreases a little bit. And it's because in solution, we lose some of these terminal ligands that somehow relax the structure and perhaps diminish, therefore, the selectivity. However, we think this is one of the most, or perhaps the most selective system based on a thermodynamic process to produce heterometallic lanthanide compounds. So we have exploited that in several ways. Here is an example of how we use mass spectrometry to trace the selectivity in solution. In color are the expected signals for the various combinations of metals. In gray is an experimental trace. For this case, for example, we prove the absolute absence of any homometallic residue compared to the heterometallic one. We see that for many of our compounds, and then we start to see the appearance of homometallic marginal, let's say, or small traces when we approach the size of both lanthanide ions. So here we go back to our gadolinium system to candidate for a 6-qubit system. So what we did is to take this compound we have published already and try to study it in detail to see whether we can promote that as a 6-qubit quantum gate, or a 6-qubit system in one molecule. So we took advantage of the versatility I mentioned before, so which would allow us to study individually each gadolinium ion if we make compounds, the corresponding compound, which on the other side has a diamagnetic metal. So for example, to study gadolinium in this position, we made a compound which has here lutetium, which is the place for the small metal. And conversely, if we want to study the gadolinium in the position for the small metal, we made the compound with lanthanum, which locates lanthanum in this other position. Therefore, we can study, by putting a diamagnetic metal in the other position, the characteristics of gadolinium in each of these two positions. So we did that, and we studied it. Then we did the characterization by different techniques. For example, Q and X-band EPR for both, let's say, gadolinium monomers. That allowed us to identify differences to the for example, to the zero field splitting of those ions between both positions. We could also compare then the magnetic response in the magnetic susceptibility of these two individual ions compared to the case with where both gadoliniums are present, where this weak antiferromagnetic interaction is identified and quantified. So with all this information, we were able to generate an approximate energy diagram that would engender these 64 states, which are the computational basis of a 6-qubit system, with the only problem that there is some crowding that somehow makes it difficult to address every single state individually. This system shows coherence, so we can detect by post-CPR the echo signals at different magnetic fields for the individual gadolinium ions, and also for the system where both metals are present. And also these post-CPR studies allowed us to compare the quantum coherence at the various magnetic fields, so for the various transitions. And for example, we can see that for the individual ions, the quantum coherence is always larger than when we have both gadolinium presence in the molecule. Okay, so with all this information, we can say that we have a candidate as at least a study case for a 6-qubit system within one molecule using transitions between the electronic levels of this kind of system. Okay, and we move now to another topic. Well, to an expansion of this topic. We discovered an evolved system by using the same principles as for the dinuclear compounds. That is the combination of 1,3 beta diketones and these kind of DP coordinate pockets. Combinations of these two coordination pockets seem to allow the generation of different coordination environments that have also a preference for lanthanides of different sizes. So by combining a ligand that is very similar to the previous one I showed with this extended ligand, we obtain a coordination scaffold, obviously serendipitously, but in the end, giving us a wonderful system that allows us to put very, very selectively, which a selectivity that is highly enhanced with respect to the previous system I showed, that put a lanthanide in the middle of this trinuclear system that is larger than the other two. So combining in one reaction two lanthanides of different sizes, we obtain this type of trinuclear system that in one pot reaction that is truly unique in coordination chemistry, because this particular one is of very, very high selectivity and doesn't require a sequential step procedure. Here I show an example of a mass spectrometry of this analog with erbium and lanthanum. It's a very pristine mass spectrum. In the original publication of this system work with these three derivatives. We've been making and characterizing, let's say, thoroughly these several other examples. And for all the cases, we have very, very high selectivity. Here is a more detailed mass spectrum of what we see when we put these compounds in solutions. In color are simulations of the various metal distributions that we can expect. In gray is the experimental trace showing only the, let's say, the expected or desired distribution, where we have the large metal in the middle and the small metals on the sides. So with this, we can do very interesting things. And for example, I'm going to show you in the last few minutes what was put forward by our colleague in Parma, Stefano Carretta, that imagined that this molecule could be used as a molecular system containing one qubit with embedded quantum correction. This circuit, which which corresponds to the evolution from left to right of this quantum correction protocol, means that here we have our qubit, here we have ancillary qubits. In our case, this is our molecule with a central metal and two external different metals. And so when we go from left to right, what we do is several pulses of EPR that are actually manipulating or generating transformations of the magnetic states at low temperature of this molecule, which correspond to specific quantum gates. For example, this pulse would generate a CNOT quantum gate between the central qubit and one of the ancilla. This is followed by the similar quantum control NAT CNOT or control NOT gate involving the other ancilla. These are 1/2 pi half rotations that are also achieved through series of pulses, EPR pulses, real experiments. This is a memory time where we can expect or not the generation of an error on this qubit. Then comes a sequence of called decoding, which is like the inverse sequence of the initial one, which is called encoding. And finally, with a specific pulse, we can undergo a 3-qubit quantum gate involving the 3 qubits of the molecule that corrects the error if there has been an error during this memory time. So this is taking our molecule and just producing a set of pulses. And this is what this error correction protocol consists of. So in order to see whether a molecule is amenable to this circuit and whether this circuit is useful or not, what we need to do is take the molecule at low temperature and characterize the Hamiltonian, obtain the parameters of the Hamiltonian at low temperature for this molecule. So in order to do this, what we do is first produce our molecule, and then produce the analogous system where we have the external ancillary without the influence of the central qubit. So having a lanthanum, which is diamagnetic metal in the middle, and study it, and doing the same thing when we want to study the central qubit by putting diamagnetic ions on the external positions. And this is real chemistry. We've done all these molecules. They are pure, that we can study and characterize them. So then we can study the ancilla and the central qubit independently, so we can characterize then the quantum gate. We did this advanced characterization in collaboration with our colleagues in Zaragoza, Fernando Luis and Olivier Roubaud. We did that using very low magnetization studies, very low specific heat studies, and EPR. And so we did this to study the qubit, to study the ancilla, so we can establish the parameters for the Hamiltonian of these two components of our molecule. Of course, we took the entire quantum gate. We did the same set of experiments, specific heat, magnetization, EPR. We also determined the quantum coherence of some of the transitions within this quantum gate. And so with all this information, we were able to generate an energy diagram that would allow us to see in which conditions we can generate or we can produce each of the quantum gates that we need to implement in order to produce this quantum error correction protocol. Okay, so with all this information, then we see this is feasible, physically feasible, and then in Parma, our colleagues used the evolution of von Neumann equation to see the evolution of the density matrix that contains information on the static Hamiltonian, the Hamiltonian associated to the different EPR pulses we are giving to the system, and then the part that is expected or associated to the errors, the probabilities of errors. So then with this, we can generate an expected plot of the probability of error. When the probability of error is above 1, that means that our system, when we implement the quantum error correction protocol, experiences less error than without the quantum error correction mechanism. So we have different plots for different quantum coherence of our molecule. We have a quantum coherence which is well, we can see approaches 1 microsecond when we have a quantum coherence. Or we compare the quantum coherence with the memory time that we with our system to evolve. So experimentally, we are addressing, or we are reaching this situation where for a long range of quantum coherences, we have advantage to using the error correction. So with this study, we completed, let's say, we have completed what we need to say that with one molecule and real parameters, it is indeed possible to implement quantum error correction protocols. So this has been published in Chemical Science. And so just let me conclude just by quickly reminding what I've been talking about today. We used heterometallic dinuclear systems to generate a potential molecule, or a molecule with which has this potentially addressable 6 qubits. And then these heterometallic trinuclear systems allow us to put forward quantum gates like quantum error correction devices in one molecule. So with this, I would like to thank the people that have been mainly involved. There are other actors in this project, but the main actors are people that did the chemistry and the characterization in our laboratory in Barcelona. Doctors David Aguilar, Leoní Barrios, Verónica Velasco, and then our collaborators that work on the advanced characterization in Zaragoza, Dr. Olivier Roubaud and Fernando Luis, and of course, Professor Stefano Carretta and his team at the University of Parma, who conceived some of these quantum gates and also performed the simulation of these protocols. So I'd like to thank the Catalan, Spanish, and European institutions for funding of these and other research projects. And I thank you for your attention. Thank you.
Thank you, Guillem. Yes, I see 2 hands. The first, it looks, call it, maybe, who is the first? Matvey, Fedя. Matvey, please.
Yeah, thank you, Guillem, very much for very interesting, inspiring talk and many interesting ideas. Just to check if I understand the things correctly, I think you measured all data, and in particular EPR data on powdered samples, right? So there was powders.
Yeah, we did both.
You did both?
Yes,
okay.
powder and frozen solution. Yes.
No. I mean, for your real spin manipulation, probably you will need single crystal in order to address selectively each particular transition, right? Because in your powder spectra, it seems that depending on orientation, they might overlap, right?
Yes. We can say that we are at the stage where we've been able to demonstrate the ability of these systems to perform these quantum gates. Mm-hmm. Now, when it comes to the moment of really implementing this and processing information, well, not only single crystals, but perhaps even go to the level of single molecules. But this is a very much, let's say, further stage. So I believe that ideally we would first move to single crystals to have a much proper characterization and perhaps to identify better the addressing issues, mm-hmm. and then eventually go further. Yes, you're right.
And you probably think of several microwave sources to hit several different frequencies at the same time, right? Or, yes. or you want to do some field jumps, or it's far ahead?
Ideally, yeah, it appears as we would go in the direction of using several sources. So, of course, we are not a spectroscopy laboratory. We are essentially synthetic chemists, but our collaborations are now, collaborators in Zaragoza are now in the process of putting together and setting up multi-frequency systems. So in order to address different let's say transitions simultaneously.
Okay, thank you very much.
Thank you.
Other questions?
Professor Fedyushkin is next.
Yeah, Professor Aromi, thank you very much. This excellent lecture. I like it very much. My question is, my question concerns synthetic chemistry. Yeah, so you showed nice approach to combine 2 different metal ions in the molecule, in one molecule. Yeah, but these ions should be different in ionic radii. Yeah? So you cannot combine, for example, lanthanum and cerium. Lanthanum and cerium, it doesn't work. It will not work. Oh?
Probably.
Yeah.
We haven't tried. Well, we've tried, but
yeah, but among the lanthanides, you can choose lanthanide in divalent state. All these examples are trivalent lanthanides. Yes?
Could you repeat the last sentence?
No, I mean, so all the examples you showed, they include trivalent lanthanides.
Ah, yes.
But among the lanthanides, you can choose divalent. So, for example, europium or ytterbium. And then you can put divalent ion and trivalent ion. That will be, the trivalent ion will be smaller and the divalent ion will be closer. But then you can combine two different lanthanide ions, which are in fact neighbors in the periodic table.
That sounds very interesting.
So maybe you can just turn your ligand to be sensitive for divalent state, for divalent ions. I think.
Well, I think this is a very interesting suggestion. We haven't tried it. We don't know whether by changing the coordination state, the oxidation state, we would preserve the same chemistry because these are a very delicate system, so to speak. We found those compounds by luck, and then once we found it, we have exploited them. And so I'm not sure that we would be able to reproduce exactly the same, let's say, procedure when we have different oxidation states. But I think it is really worth trying it, and this is a very interesting suggestion. So thank you very much.
No, I mean, for example, lanthanum plus 3, trivalent lanthanum is approximately the same as samarium plus 2. So you may replace diamagnetic lanthanum with paramagnetic samarium plus 2.
Sure. But then as soon as we change the oxidation state, then we change the charge balance, and perhaps the system doesn't work the same way. But we haven't tried it, so I cannot say that it's not going to work. So I think it's very interesting.
It's just from synthetic point of view. Yeah, thank you.
Thank you very
And
much.
the last question from Professor Novikov. Valentin, please.
Thank you. Hi, Guillem, very nice lecture. I wonder if you thought about using luminescence for readout the state of your Q-gate afterwards. So it should be possible, I think. So if you, for example, measure luminescence over different range of magnetic fields at different temperatures, it should give some access to spin dynamics.
Hi, Valentin. It's very nice to talk to you. Thanks for the question. Of course, I guess in theory, the luminescence should allow you to read out your spin system. I believe that you have to use very low temperatures, and so also reach a setup that will allow you to perform this experiment. But of course, with the setups we have in our lab, we're not able to do this. But I think it would be also a good possibility that we explore.
Just so you know, but not far from you in Montpellier, Jerome Long is measuring luminescence at low fields and low temperatures and high magnetic fields. So it should be possible to see.
Absolutely.
It's possible.
Yeah. Also, I believe the people in Lyon are also very, very specialist on this topic, and so we started some collaboration on studying and exploiting the luminescence of the heterometallic systems on its own. So for issues of charge transfer and so we can go also on this direction.
Okay, thank you, Julian. And thank you again. Dear colleagues, let me thank again all our speakers at the fifth session. And thank you so much for your scientific so important installment. Now we have a very short coffee break or tea break for 20 minutes. We start next session at 11 Moscow time. Thank you, everybody. See you in 40 minutes.